Hello everyone. So today we got to go over section 3.1, inverse of a relation. So some background, we are going to look at how to isolate the variable in the following equations. So example 1a, we have x equals to 5y minus 3, and we want to isolate the variable y. So the first step here is to add 3 to both sides, and we have x plus 3 is equal to 5y. And then afterwards we can divide both sides by 5, so we have y is equal to x plus 3 all over 5. Similarly, for example 1b, we will first multiply both sides by 5, so we have 5x is equal to 4y plus 1. Then we'll subtract 1 from both sides. 5x minus 1 is equal to 4y. And finally, we will divide both sides by 4, so we have y is equal to 5x minus 1 all over 4. So of course we can extend this idea to quadratic relations, like we have in example C and D. So here we'll subtract both sides by 1. X minus 1 is equal to 2y squared. Then we'll divide both sides by 2. So x minus 1 all over 2 is equal to y squared. And finally, we can square root both sides, so y is going to be equal to both the positive and negative square root of x minus 1 over 2. So let's try to write it this way. Okay, that works. X minus 1 over 2. Right, it is important to make sure to have both the positive and negative square root, as we will see why that is a little bit later. All right, moving on. Example D. We'll add 3 to both sides first. So x plus 3 is equal to 1 half y minus 1 all squared. Multiply both sides by 2, so this could be written as 2x plus 6 is equal to y minus 1 squared. Then we can square root both sides. Again, keeping both the positive and negative square roots. Is equal to y minus 1. And finally, we can add 1 to both sides, so y is equal to 1 plus or minus the square root of 2x plus 6. Okay, so the reason why we are looking at isolating the variable is to examine inverses, and has to do with reflection over the line y equals x. So for a function y equals f of x, the graph x equals f of y is the is the image of the graph y equals f of x after reflection on the diagonal y equals x. They are inverses of one another, so if the point PQ was on y equals f of x, then the point QP will be on the inverse. Okay. So when the inverse is also a function, which is not always the case, the notation y equals to the after the negative 1 as it says right here, of x is used to denote the inverse function. So it is important to note a couple of things here. Number one, all functions and relations have inverse. However, not all inverse of functions are themselves functions. Just going to take a moment to write that down. And we'll see some examples of inverses that are functions and some examples that are not in the following. So just ran out of space there a little bit. Alrighty. So it says here to graph the function y equals 3x minus 6 and then its inverse. So let's graph the original function. Let's see, 3x minus 6. So that would have a y-intercept of negative 6 and a slope of 3. So something that looks like this. All right. Go ahead and draw that in. So this would be the line y equals to, oh, actually, let's put it here, y equals to f of x, and that f of x is 3x minus 6. Okay, and then if we are to graph its inverse, we should probably find the inverse first, and that is done by switching x and y. So we have x is equal to 3y minus 6. So that would be add 6 to both sides. Next step was 3y, and then we can divide both sides by 3. So we'll have y is equal to 1/3 x plus 2. All right, so the y-intercept is 2, and then the slope is 1/3, something like this. I think we draw in the line there, just like that. And so we can see here that the inverse is also just a straight line, so it is going to be a function. So we can actually use the notation y is equal to f to the negative 1 of x to the inverse notation, and that's going to be equal to 1/3 x plus 2. Also of note is the fact that it is a reflection over the line y equals x. So we'll draw in here the line y equals x just to emphasize that they are reflected on the line diagonal. Alrighty. So this is an example then of a function whose inverse is also a function. Let's examine another one of these. Alright, so here we have a piecewise function made out of 3 line segments. So we are going to graph the inverse and then determine the domain range. Okay, so let's see here. So there are 4 key points to look at. Their coordinates are -4, -2, -1, 4, and then here we have 3, 2, and finally 6, 3. So using the definition of inverse that we had, we are going to switch the x and y values and plot those points. So the first point will be -2, -4, which will be down here. Just going to add in the label. Next point will be 4, -1. So here it is. After that, the point 2, 3 will appear on the inverse. And finally, the last point is 3, 6. So up here. Okay, so then we connect these 4 points together, like so. And we have graphed the inverse. Notice that the inverse is not a function, right? Because it doesn't pass the vertical line test. So if we were to draw a vertical line here, for example, it fails the vertical line test. So make a note of that. Inverse is not the function. Okay. But it's still a good idea to draw in the diagonal y equals x to once again emphasize the reflection aspect of the function and its inverse. Okay, so about the domain and range of the function and its inverse, the domain of the function, just going to write it down here, was -4 to 6. And then the range is -2 to 4. Right? We only have to look at the minimum and maximum values for both x and y. Now the domain and range of the inverse, so the domain is -2 to 4, and the range is going to be from -4 to +6. So notice that the domain and range basically just switches when we go from the function to its inverse. So here, draw some arrows in to indicate the switch. All right, so we now have seen a function whose inverse is also a function, and now we have seen a function whose inverse is not a function. And finally, we have yet another example here. So we have the graph y equals to 2x squared minus 3. Let's go ahead and draw that in using a table of values, I guess. So this would be x equals 0, y equals -3. And then when x equals to positive or -1, we have y equals -1. And when x is equal to 2, 2 squared is 4. And then, times 2 is 8, minus 3 is 5. Of course, the same thing for the negative values here in this case. And we can go ahead and graph the parabola that results from all this. It's going to be careful here. Drawing parabolas is always a little bit difficult, so just going to do our best here. Okay. Just going to draw the other side. Just making sure that the base of the parabola, the vertex, is not too pointed. So one thing we can do here is just erase this part and draw it so it has a smoother transition. That didn't really work. Okay, let's do it this way. So it doesn't look like it's a sharp turn because it isn't a sharp turn. All right, so it says the graph, the inverse. there's a couple of ways of doing this. We can either just go ahead and find the points that are on the original function, like what we're doing right now. So there are 5 points that we used for the graph. And of course, from our understanding of inverses, we just have to switch the x and y coordinates and plot those points. Go ahead and do that. So we have -3, 0, and then -1, 1, -1, -1, and then 5, 2, and 5, -2. So just by looking at what we have drawn, you can see that the inverse is not a function, right? This is not going to pass the vertical line test. But let's just draw that in to continue our discussion for this example here. Right, can do our best when it comes to drawing parabolas. It's always a little bit difficult to get a nice smooth curve. All right, I think that's good enough for our purposes. Okay, so says graph the function as inverse, which is now done. Would be good to label it. So this is the function in purple, and the parabola kind of on its side pointing to the right is the inverse. All right, and then the example asks, how should the domain be restricted so that the inverse is also a function? So what we'll notice here is that if we are to split this parabola into 2 parts, I'm going to use a different color here, like so. The left-hand side of the original parabola corresponds to the bottom half of the inverse. So this side here, I'm just going to draw it temporarily in, on the left, corresponds to the bottom half of the square root function, which, well, not a square root function, but the inverse relation. Okay, and likewise, the right side of the original parabola corresponds to the top half of the inverse. So that would certainly be a way to restrict a domain. Okay. Now, an important key to note here is that when it says to restrict a domain, it's always talking about the domain of the original function. Right, so we start by restricting the domain of the original function, so the resultant inverse is a function as well. It's very important to note that technicality. There are 2 ways to restrict the domain. Well, there are 2 main ways. There are more, but the 2 that are the most intuitive are the ones that we're going to examine. So before we continue, let's also look at the algebraic part of all this. Haven't used red in a while. So again, we are going to find the inverse algebraically. So x is equal to 2y squared minus 3. So we have x plus 3 is equal to 2y squared. And then, of course, we'll divide both sides by 2. So x plus 3 over 2 is equal to y squared. All right, of course, then the next thing to do is the square root, the function. Sorry, not the function, the both sides of the equation. It's very important that we be very clear about the words and the vocabulary here. All right, So y equals to positive or negative square root of x plus 3 over 2 will be the entirety of the inverse graph that we have on the left, both the top half and the bottom half. And as we stated, there are two ways to restrict the domain. So one of the ways to restrict the domain is to let x be greater than or equal to 0, okay, which will produce the right half of the original function only, so this part only, right, because that's where x is greater than 0 on the original function. And that would correspond to the top half of the inverse. So the inverse would just be the positive square root. All right, so likewise, if we are to restrict the domain with x is less than or equal to 0, then the inverse will correspond to the bottom half, and that will be the negative square root. Let's go x. Oops, sorry about that. So this would be x plus 3. Then let's draw in blue here. Over 2. Okay, so that's how we can restrict the domain of a function so the resultant inverse is also a function. Right, so, and that's all we have for inverse of relation. The key here is that how to find inverse both graphically and algebraically, and also the restricting domain portion about inverse as well. And that's all we have for today, so thank you for listening.